Welcome to the first problem in our 5-5 practice set. A space shuttle releases a satellite into circular orbit at 780 kilometers above the Earth. How fast must the shuttle be moving relative to the Earth's center when the release occurs? All right, so in the lesson 5-5, we derived an equation for finding the velocity required by a satellite at specific distances from the center of the Earth. That equation was this. The velocity, of course, being tangential, is equal to the square root of the gravitational constant times the mass of the Earth divided by the distance r, the radial distance r from the center of the Earth. Now the thing is that this problem only gives us the height above the surface of the Earth. So it says that the satellite is released at some height, which is 780,000 meters. Okay, I quickly converted that from kilometers to meters. But it doesn't give us actually anything else for what's actually in this equation because h is not r. In order to get r, we need to take h and we need to add it to the actual radius of the Earth. Okay, so quick calculation there. If the height is 780,000 meters, we're going to go ahead and add that to the radius of the Earth, which is going to be, in scientific notation, would be 6.38 times 10 to the power of 6 meters. All right, I'm going to give that quick calculation in scientific notation as well. You can double check it yourself if you want. It's going to be 7.16 times 10 to the power of 6 meters. All right, so that's what's going to go into our equation for the velocity of our satellite. All right, 7.16 times 10 to the power of 6. Now, we also should keep in mind the mass of the Earth. It's most generally given as 5.98 times 10 to the 24th kilograms. Okay, of course, that's SI, so we can leave that just how it is. And then another thing that we're going to need to remember is big G, the gravitational constant. That's going to be 6.67 times 10 to the negative 11. And if you'll remember, the units are a little funky. It's just whatever we need to make the newtons work. So it's going to be Newton meters squared per kilogram squared. So that's going to be Newton times a meter squared per kilogram squared. All right, now it looks like we have everything we need in order to plug into our expression here, big G, mass of the Earth, and the radial distance r, in order to get the velocity. So let's just start plugging stuff in. I like to keep units with me as much as I can just to make sure everything is checking out properly. So this is going to be a big square root sign. I'm going to plug in 6.67 times 10 to the negative 11 Newton meters squared over kilogram squared. I'm going to multiply that by the mass of the Earth, which is going to be 5.98 times 10 to the power of 24. I'm going to cut the units here because I do not have enough space. I'm going to divide that by 7.16 times 10 to the power of 6. And if I go ahead and plug all of that information into my calculator, then I should be able to take to a reasonable number of significant figures. V is equal to about 7,460. That's 3 significant figures. If you wanted to keep, if you took it from the calculator to like say 5 significant figures, you probably got something like 7,463.7, depending on what you kept and what you left off as you were calculating. But to 3 significant figures, we're going to say 7,460 meters per second. That's the velocity that the satellite would need to be in order to start its uniform circular orbit at a height of 780 kilometers above the Earth. See you in the next one. Very similar to the previous problem, the second problem in our 5-5 practice set says calculate the speed of a satellite moving in a stable circular orbit about the Earth at a height of 4,800 kilometers. Now, again, with the height above the surface of Earth, doesn't tell us everything we need to know. We also need to add the radius of Earth in order to find the radial distance between the center of the Earth and our satellite. So again, what we calculated in lesson 5-5 is that in order to find the velocity required for a satellite to stay in orbit, we're going to have to set that equal to the square root of big G times the mass of the Earth over the radial distance between the satellite and the center of the Earth. So that r is not going to be the height from the surface of the Earth. It's going to be the height from the surface of the Earth plus the radius of the Earth. So it's given the height to be 4,800 kilometers. So I'm going to go ahead and plug that in for H. R is equal to, let's do 4,800,000 meters. That's going to be the conversion from kilometers to meters. In fact, one thing that you'll want to do and get used to is go ahead and write that in scientific notation. In this case, that's going to be 4.8 times 10 to the power of 6 meters. And we're going to add that to the radius of the Earth, which is one number that you're going to want to get comfortable with remembering. That's going to be 6.38 times 10 to the power of 6 meters. All right, very good. If we go ahead and add these two numbers together, you'll get something like a radial distance of 1.118, maybe 1.12 if you want to go ahead and take 3 significant figures, but we're still in the middle of our calculations, so I'm going to keep an extra significant figure there. 1.118 times 10 to the power of 7 meters. Okay, so now we have R, and of course we know the mass of the Earth, and that's another number that you're going to want to get comfortable with remembering. That's going to be most usually 5.98 times 10 to the power of 24 kilograms. Everything is currently in SI, so we're very good. And then the gravitational constant is going to be another one that you're going to remember, but usually given to you on things like formula sheets and everything like that. 6.67 times 10 to the negative 11. And the units here are a little bit weird just to keep everything working as newtons in Newton's law of universal gravitation. The units are going to be newtons meters squared per kilogram squared. All right, that said, we have now all of the information we need in order to plug straight into our equation for the tangential velocity required by our satellite moving in circular orbit. So I'm going to go ahead and start plugging things in. I'm going to hold the units here because I'm going to run out of space on the left side, but generally speaking, it's best practice to keep your units in your calculations just so that you can check off that everything is canceling out the way it should be canceling out and you're getting meters per second at the end. So V is then equal to 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th over 1.118 times 10 to the 7. If we take the square root, all of this, that should give us our velocity. And if we go ahead and pop all of that into your calculator, then you should get a velocity of 5,973.0 meters per second. Now, of course, we'd only want to take this to 3 significant figures because that's the best we have in our calculations. So that in that case, it would be something like 5,970. If you make the argument that it's just 2 significant figures, 5,000, I guess 6,000 would be perfectly acceptable of an answer here. That said, good luck, and I'll see you in the next one. Welcome to the third problem in our 5-5 practice set. A 12-kilogram monkey hangs from a cord suspended from the ceiling of an elevator. The cord can withstand a tension of 185 newtons, and it breaks as the elevator accelerates. What was the elevator's minimum acceleration? All right, so first off, to understand this problem fully, I want to recommend that we consider Newton's second law of motion. So that means that the force created is equal to the mass of an object times its acceleration. Okay, so the mass of an object in question here is just the 12-kilogram monkey. So if I plug in 12 kilograms for mass, and then I plug in 9.8 meters per second squared for acceleration, which would just be the force due to gravity, this gives us only about 117. Let me see if, in fact, it gives us exactly 117.6 newtons. So that means if the elevator is stationary and the force that the monkey exerts on the cable is just force due to gravity, then it won't be enough force to actually break the cable. It won't be enough force to break the cord. But then we ask what acceleration would be required in order to break the cord. So I'm going to, continuing on with Newton's second law, set force equal to 185 newtons because that's what we need in order to be able to break the cable. The mass doesn't change. It's still the 12 kilograms of the monkey. And then we're going to find out what acceleration is going to be required in order to break that cable. This extra acceleration is going to come from the elevator accelerating upwards. If you recall, if the elevator were accelerating downward with the monkey, that would decrease the monkey's force on the cable. It's the elevator accelerating upward that would kind of add to the acceleration and the force that is being applied to the cord. Now, if I divide both sides by 12 here, 185 divided by 12 gives us something about 15.42 meters per second squared. So we're going to need an acceleration, a total acceleration of 15.42 meters per second squared if our mass is a 12 kilogram monkey. So when the elevator accelerates upward, it effectively increases the gravitational pull by the monkey. So imagine that you're in a car that suddenly speeds up. You're pushed into your seat. Similarly, the monkey feels heavier due to the elevator's acceleration, even though its actual weight remains the same. This apparent increase in weight increases the tension in the cord. If this tension exceeds the cord's limit of 185 newtons in this case, it will break. Okay, so what I'm saying is that effectively, if acceleration due to gravity is 9.8, then the acceleration that the elevator is going to need is the difference between 15.42 and the 9.8 that we have from gravity. In this case, the acceleration that the elevator would need is about 5.61 or about 5.60 meters per second squared in the upward direction. All right. If you have a little bit of difficulty understanding why this is the case and why it necessarily has to be upward, please, I'd love to elaborate a little bit further. Go ahead and leave a comment or shoot me an email. But good luck, and I'll see you in the next problem. Welcome to the fourth problem from our 5-5 practice set. Two satellites orbit Earth at altitudes of 7,500 kilometers and 15,000 kilometers above the Earth's surface. Which satellite is faster and by what factor? Okay, so the interesting thing about this problem is that it's just asking about a factor. So I can kind of set them up as a ratio. I can say that the velocity of the satellite with the smaller orbit has some factor with the velocity of the satellite with the larger orbit. The larger orbit, of course, referring to the 15,000 kilometer above Earth's surface orbit, and the smaller orbit referring to the 7,500 kilometer above the Earth's surface orbit. And because we do already know equations and expressions for finding the velocity of a satellite, then we can go ahead and set that up as ratios of those equations as well. The expression, of course, being the square root of big G, mass of the Earth, over the radius or the radial distance between the satellite and the center of the Earth. So this is going to be the radial distance of the smaller orbit. And I'm going to put this over the same expression, but with the radial distance of the larger orbit. Now, of course, this is going to test our algebra skills a little bit, but if you have the square root of the numerator and the square root of the denominator, that's the same thing as the square root of the whole ratio. So before I even rewrite this again, I'll notice that I do have G on top and bottom and mass of Earth on top and bottom. We're taking the square root of both, so we can go ahead and cancel those terms out, or those factors out. That said, what we're left with is that we have the square root of 1 over the smaller radial distance over the square root of 1 over the larger radial distance. And again, still testing your algebra skills a little bit, this would be the same thing as the total square root of the larger radial distance over the smaller radial distance. All right, so this isn't physics necessarily, just a little bit of algebra simplifying our expressions here to this important point right here. Okay, so now we need to figure out what those radial distance are, because they're not just the numbers that are given. Okay, the larger radial distance is going to be the radius of the Earth plus 15,000 kilometers or plus 15 million meters. So that's going to be equal to, and we're going to do this in, we can go ahead and keep this in kilometers actually. It's not going to make much of a difference because we're just going to be taking the ratio. So the distance or the radius of the Earth in kilometers is just 6,380 kilometers. And then plus, of course, for the larger radial distance, plus 15,000 kilometers. All right, that's going to give me a larger radial distance of roughly 21,380 kilometers. All right, for the smaller radial distance, it's going to be that same Earth's radius, the 6,380 kilometers, plus 7,500 kilometers. That's going to be equal to 13,880 kilometers. Now we have everything we need to plug into our ratio and find the factor difference between the speeds of these two satellites. So I'm going to go ahead and plug that in here. It's going to be the square root of 21,380 kilometers over 13,880 kilometers. And bringing the answer all the way down to the bottom of the page, that's just going to leave us with 1.24 when I plug that in the calculator. And so then we could say that the two orbits, or more specifically, the orbit of the satellite with a smaller orbit has a 1.2 times faster orbit than the satellite with a larger orbit. All right. So that means that the satellite with the smaller orbit is moving with a faster tangential velocity. All right. Good luck, guys. I'll see you in the next one.